Okay, so we're going to start with the second QPE session. And,
is that a series?
Giovanni Miniutti, who works at the Central for Astrophysics. Works at the Central Astrobiology in Spain, and is going to talk about updates on QPEs in GSN 069. So just as a reminder, the talk is in between the 25 and the 30 minutes.
Okay, so thanks. Can you hear me well? Yes? Good? Okay, so thanks a lot for having me. It's a pity that I could not join you in person, but that's life. So I will share a little updates on the first QPE source GSN 069. Here I list my main collaborators on this. Richard Saxon is the second one, was the one who first detected this source in the X-rays, thanks to an XMM Newton slew, which means when the telescopes slews from one target to the next. Margherita Giustini, after the detection of QPEs in this source, we went into the XMM archive and selected one source that looked particularly promising, and Margherita was the one who discovered QPEs in this second source. And then Ricardo, you all know about his work on eROSITA and the detection of further two sources in active galaxies. So, oops, doesn't seem to change. Okay, so this is the field of this galaxy. This little insignificant dot at the center is GSN 069, and you see on the right hand side an optical spectrum of this source taken just after it went in outburst in 2010. What you see is a clear Cipher2-like spectrum. So with narrow line ratios clearly indicating an AGN nature and with no broad lines at all. The surprising thing about this is that this is a very strong Cipher2. So it's not just a borderline AGN, it's clearly an AGN, one of the strongest among the QPE sources. And the strange thing is that, of course, there is no absorption at all in the X-ray band. And this source showed exactly the same optical spectrum since 2003. When Rosat, well, in 1994 showed only an upper limit for its X-ray emission, then showed exactly the same spectrum in 2010 when it went in outburst, and then again 10 and even 10 years later that it went in outburst in 2022, it shows exactly the same spectrum. So this is a Cipher2 galaxies, and we have to keep that in mind because there's something that we have to understand about it. About QPEs. So as I said, the source was first detected in an XMM Newton slew in 2010. And then we suspected it was a sort of long-lived QPE, TD, sorry, long-lived tidal disruption event. Although it took some time to get there, because during the first year or so, the flux was rather stable. It didn't decay like an ordinary tidal disruption event. But after a while, we saw this decay and we started following it up in the X-ray band. So what you see here in gray and black are the first two pointed X-ray observations. And I show the light curve here, the first one and the second one. And you see very little variability. I mean, some variability in the first observation and an almost constant flux level in the second one, which was taken about 4.5 years after the initial detection. And then after a while, precisely about 9 years, 8.5 years after the first detection, we got an XMM Newton observation just to follow up this TD-like behavior, and we detected these QPEs. We then started follow-up campaigns, and we detected other QPEs in the following months. This blue and yellow observation are separated roughly by 6 months. Okay, so this was the initial detection of QPEs in this source. One thing that is worth mentioning is that so far, at least, QPEs are an X-ray only phenomenon, in the sense that we have looked as hard as we could. Probably we can do better and we will do better, but as hard as we could, thanks to the optical monitor on board an XMM, we have looked at light curve, simultaneous light curve in the X-rays, optical and UV. and we didn't see any QPE nor in the optical nor in the UV. So this appears to be really confined to the X-ray regime, or completely overwhelmed by other emission like galaxy, stellar-like emission, or disk-like emission from the accretion disk in the other wavelengths. Okay. So some of the properties of the QPEs specific to GSN 069 are a very clear alternating pattern of both the intensities, which we see on top. So these are strong, let's say, QPEs that are always followed by a weak one, then a strong one, a weak one, and so on. And the same happens for the separation in time between consecutive QPEs. So what we call recurrence time. So this is the recurrence time between these two QPEs. You see that it is longer than the following one, then long, short, and you see also a sort of modulation on some, this time scale here, one observation is about 1.5 days. So you see a sort of modulation that seems to be present on days time scales, okay? So the period, as you can see, the recurrence time is not perfectly constant. It oscillates with a fluctuation of the order of few percent. So this is not a strictly periodic phenomenon, but just a quasi-periodic one, okay? Another interesting thing is that if you fold these light curves, so these are the three observations where QPEs were detected, folded at the recurrence time between QPEs. So you just see the strong, I mean, two QPEs separated by a phase of 1 because we have folded them. So this is just twice the real interval, which is 0 to 1 in phase. Just for clarity, we show 2 intervals, but it's just 1. And if you model this light curve in the easiest possible way, which is a constant for the quiescent level plus Gaussian for the QPE, what you see as residual of this kind. In all observation, there are residuals that really look like sinusoidal. Actually, they are extremely significant from a statistical point of view, but more than being significant in one given observation from a statistical point of view, the important thing is that they are always there in all observations with the same period as the recurrence time between QPEs. So this is period 1 in phase space, so it is exactly the same period as the separation between QPEs, okay? This QPO-like variability peaks with a delay with respect to the preceding QPE, which is about 10 kiloseconds, 3 hours or so. And moreover, the intensity of the QPE, you see there is some drop here in the intensity of the QPE. There is a similar drop in the intensity of this sinusoidal variability. And basically, the ratio between the two intensities keeps constant. It's epoch independent, basically. It's always the same, at least in these observations. So about the individual QPE. So here, what I show is again the profile of one single QPE folded. So this is actually the combination of several QPEs, but just to increase the signal to noise, all QPEs do exactly the same, which is color-coded with respect to rise phase, peak, and decay phases. And what I show on the right-hand side are 2 plots. On the top, it's the L to LT relation. So this is bolometric luminosity of the QPE, in different phases as a function of temperature, okay? So what you see is that the QPE starts to increase in flux and also in temperature, then it peaks at slightly lower temperature and then decays. This is the anti-clockwise behavior, right? And what you see here are 2 dotted lines are LT to the 4 relations. So basically, while the rise is okay with an LT to the 4 relation, the decay is not, okay? And actually, if you believe that this is thermal in origin, and I can assure you that all indication that we have so far from an observational point of view seem to be to indicate that these are really thermal emission. If you believe that this is black body-like emission, you can compute, of course, the radius or the area from which this X-ray emission comes from. And this is shown here, the radius of the black body emission, assumed, I think, as a sphere or as a disk. Now I don't remember exactly. Superimposed with the with the profile of the QPE. So you see, exactly because it follows in the initial rise, the L to the 4 relation, you see a constant initial phase at constant radius, and then an expansion by a factor 2 or 3. Okay. This, sorry if I can go back. So this means that basically the QPE starts with being associated with a given area, and then this area expands, which tells us that the emission is most likely coming from something like a shock instead of direct accretion of some excess matter on the black hole, right? The typical radius here that you see is basically the radius of the sun, few times 10 to the 10 centimeters, okay? So these are the typical characteristics. Now, if we focus on the peak of the QPE emission, we can, instead of looking at the individual QPE, to look at all QPEs we have observed so far in GSN 069. And we plot the same temperature on the x-axis versus bolometric luminosity on the y-axis. So these are all the QPEs observed at peak. And the dotted line, again, are LT to the 4 relations. So basically what this says is that the peak emission of QPEs in different QPEs that have different luminosity, different temperature, not that much, but a little bit different temperature and luminosity, is consistent with being always roughly the size of the sun, okay? It is roughly consistent with the peak luminosity of the QPEs, always associated with a region that has a similar size and the size of the order of the sun. Now, if we take a light curve of one QPE, of one orbit, this is 1 XMM Newton orbit with 5 QPEs from GSN 069, we have then looked at what the quiescent level was doing. Okay, we have several observations covering 12 years, so we can try to understand what the quiescent level itself is doing. Okay, so this is the overall light curve over about 12 years. In red, you see XMM Newton pointings, and in blue, Swift observations. And you can see an initial decay, not by much. This is bolometric luminosity, not by much, a factor of a few in 9 years, and then a clearer brightening. So we have tried to model that, and we use the simple, very simple phenomenological TDE-like light curve models. So we imposed a Gaussian rise and a power law decay. In this case, we choose an index for the decay of 9/4, but I can tell you that 5/3 or 1/5/12 or an exponential decay is fine as well. So this is just to show that the data are consistent with possibly 2 tidal disruption events in this source. We also detect some indication of 2 precursors here, not highly significant, but they are just observed when the initial rise is. So they might perhaps be associated with these famous circularization shocks that give rise to accretion disk then formation. Anyway, this is just to say that the light curve in the past 12 years is consistent with 2 repeating partial TDEs, 9 years apart, and that have rather peculiar properties in the sense that they are very much long-lived. The decay is only by a factor of a few in years. So this is not the typical one, okay? So perhaps they could be associated with the expected time scale and fallback rate for an evolved star, which is partially disrupted, was part of WOS envelope is disrupted at very large distances, and so perhaps give rise to this long time scale. But this is obviously not a unique interpretation. You can interpret that also as normal variability, let's say, which happens to be to have this peculiar shape. Okay, assuming these are 2 partial TDEs, we can integrate this light curve and obtain the disrupted mass, which would be around half solar masses in the first tidal disruption event and about 10% in the second one. Orders of magnitude with lots of uncertainties. Then we can ask where QPEs were detected during this long-term evolution. So here I show the same light curve as before, and in color you see all observation with QPEs. This is on the right-hand side is just a zoom of this same light curve. And basically what happens is that, okay, let's take this one as a representative of the first 3, this one here. Then we will have a look at this black observation. All these black observations look exactly like this. Higher flux, you can see, higher count rate, but no QPEs at all. And then you have this green data point at the end of our monitoring where QPEs appear again. So at first sight, you would say they have disappeared and then they have reappeared. Is there any variable that we can associate it with this behavior? Well, if you look a little bit in more detail of the overall light curve, what you see here in gray are observations that are too short to detect QPEs, so we ignore them. While black and colored ones are all long enough to detect QPEs. And you can see that the black ones all cluster at high luminosity and the colored one all cluster at low luminosity. So it looks like there is a bolometric threshold or Eddington ratio threshold for the appearance of QPEs, that QPEs only appear below a certain threshold, okay? If this is correct, and it is probably too early to say because we need more data here, in the sense that we only have that observation, the green one, the last one, that says that they have come back at low luminosity. We are waiting for observation here showing that there are no QPEs or that there are QPEs. So for now, we can say that it looks like there is a connection between the disk properties and the QPE properties, in the sense that when the disk is accreting at high mass accretion rate, QPE disappear, okay? So we have looked a little bit in more detail on what is associated with the disappearance of the QPEs in a purely observational, from a purely observational point of view. So here what I show on the right-hand side is the relative amplitude between the QPE and the quiescent level. So how strong is a QPE with respect to the quiescent level as a function of the temperature ratio between the QPE and the quiescent level. The quiescent level is very well described by a standard disk, okay, with a given temperature. The QPE is very well described by a black body with a given temperature. You take the ratio and you plot this amplitude versus the temperature ratio. You see that obviously, as the temperature ratio goes down, the amplitude as well goes down. And this is easy to understand because actually QPEs only carry like 10% of the bolometric luminosity. So when the temperature of the QPE is exactly the same as the temperature of the disk, you would see just a little fluctuations, a 10% fluctuation in your light curve. You would not see a huge QPE. So basically what this analysis says is that when the temperature of the QPEs is similar to that of the quiescent level, QPE tend to disappear. So models should try to have this characteristic built in, so that at high mass accretion rate, the temperature of the QPE tends to the temperature of the quiescent level, so that at high mass accretion rate, QPE disappear, okay? So this is a little constraint that we put on the models. If you don't have this condition, it will be difficult to explain why you don't have QPEs in these black observations at high mass accretion rate, but that are long enough to actually be able to detect QPEs, okay? So now I would like to focus on the last observation, so this green one. I just want to remember you that we interpret this very long-term light curve as two partial tidal disruption events. So if we take an observation here and then we will take an observation there, we will go from just before the second tidal disruption to just after the second tidal disruption. And in between, we don't have any QPE, okay? So there is a pattern before the second TDE, no QPEs anymore at peak, and then a different pattern I will show you now after the second TDE. So this is the new observation that we had collected not so long ago. And what you see is that if you align these two strong QPEs, there are two clear facts. One is that the weaker QPE is very much weaker than it was before. So the contrast between the strong and the weak QPEs is much increased. But perhaps most importantly, the quasi period is gone, okay? So this separation that was shorter than this one, as I said, there was some alternating patterns, so long recurrence time, short recurrence time. It was shorter by 5%, 6%. Now, if you take this short recurrence time and you compare to this, that is just a lower limit to the long one, this is more than 30%. So something has changed in the properties of the objects or the mechanism, the processes that make QPEs, so that basically we lost this quasi-periodicity, which means very similar recurrence time, although with some fluctuation and an alternating pattern. We now have possibly a very long recurrence time and a very short one. Now, it will be interesting to know where this other peak is, if it's just here, or if it's aligned with that peak, which will be very interesting. We have collected an observation already that is long enough to detect at least 3, if not 4 QPEs. So we will have results soon, but we don't have the data yet. The observation has been performed, it went well, but we have to receive the data yet. Okay, so it will be interesting to know where this peak is aligned with the other strong one, and so only this one moved around, or if the whole pattern changed. So from the whole discussion that I tried to summarize, I hope that we will have time for discussing more. Any model that tries to discuss the physical origin of QPEs, and I will talk here only about GSN 069, but of course there are other constraints on other sources as well. But in general, any model should not ignore the presence of an accretion disk. This appears to be important. It appears to even to be able to explain or to be, let's say, the origin of why QPEs sometimes are not detected. So an accretion disk is there for sure in GSN 069, and it has to be taken into account. Then, of course, any model should try to explain why this alternating intensity and recurrence time properties of the GSN light curve. It should try to account for the presence of the quasi-periodic oscillation of the quiescent level, more or less at the same period as the QPEs with a certain delay. This might be secondary QPEs, perhaps, broader long-lived QPEs, or a genuine oscillation of the quiescent level itself, of the mass accretion rate of the disk, basically. So this has to be investigated. It should explain the QPE energy dependence. So this hysteresis in the LT plane, which with a rise and then a decay, but you can have different temperature for the same luminosity. So there is hysteresis. And should also try to at least explain why we see an expanding region that has at peak more or less the radius of the sun. Okay. And also be consistent with the fact that the temperature, the contrast in temperature between the QPE and the disk should go to 1 at high mass accretion rate. Now, as for the newest observation, there will be more challenges, I'm sure, more things that we don't understand. But at least we can say that we have to understand why after a tidal disruption event, possibly this is the reason why, I don't know. But this is phenomenologically what you see is that after a likely tidal disruption event, a new phase appears with different timing properties, with different intensity ratio between the QPEs. And stay tuned because we will have more about the real pattern soon, very soon. So I don't want to go into any of the models because you have a session dedicated to it with much more expert people than me. I just list here the many models, or I hope all the many models that have been proposed, or at least some of them. I just want to highlight that most of them invoke an orbital origin for QPEs with a extreme mass ratio system. So a supermassive black hole at the center, the accretion disk fine, but then something else with much lower mass orbiting around it. And the only thing I want to say about it is that this has great potential, not only for gravitational wave, multi-messenger astronomy, and this kind of things, but just as a space-time probe. It's a test particle going around. And if you think about what we have done with what they have done with the S2 star around the Sagittarius star, which has a 16-year period and a 17 light hour pericenter distance. In this case, the typical, let's say, QPE system has a 20-hour period and less than a quarter light hour pericenter distance. So this is not because we like to establish records. This is just to highlight that all relativistic effects that are almost starting to be seen in S2, if we are able to follow this light curve for long enough, will show up very clearly in this system, in this kind of system. So I'll end up here. I have many more slides to show if you want, but I think it's better if we go for some discussion. Thank you. Thanks a lot.
Thank you very much. Any questions?
You highlighted that when GSN 069 is more luminous, you don't really see the QPEs, but they probably should be there at some 10% level or something like that. Are you sensitive to smaller amplitude fluctuations like that?
So I'm not sure if I have the answer here somewhere, perhaps. I'm not sure if I put it there in the slides, but it's better to show you if I have it. No, I don't. Okay. So in one of these observations where no QPEs are present, actually we see a flare of even 20%, probably 15-20% at the 10 to 15% level, and we have analyzed it in exactly the same way we analyzed QPEs in general. And so what we found is that it has a temperature that is very, 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 very similar to the disk, just slightly above it, and a luminosity that is 10%, so just above detection threshold in this case. So it looks like there is at least in this observation where no QPEs are present, one very, very weak QPE that complies with all the requirements, all the things we have said. So the fact that the luminosity goes down as the temperature approaches that of the disk. For the rest, it's tough to say. I think we could do some better analysis to identify QPEs, but the fact that the timing properties between before and after changed don't allow us to look for knowing the period where to look at. So for example, folding light curve and to highlight some very low signal to noise fluctuations. But anyway, I think that we have some clues that in fact QPEs are there, but they are very weak during observation at high luminosity.
Are the QPOs present during the high luminosity?
No. No, QPOs are at least very clear. QPOs are only present during observation with QPEs. Actually, even in the last one, the last observation that I show with only 2 QPEs and different timing properties, it looks like there is a QPO, which we cannot claim with high significance simply because it's one observation. The period turns out to be very similar to the exposure, so the total duration of the exposure. So it's not significant. But it looks there. It looks that it's there. While in observation where no QPEs are present, there's nothing striking.
Yes, there was some discussion yesterday about UV, the possibility of UV flux from QPEs. I know you mentioned you're not detecting them optically. Do you have any evidence for ultraviolet emission at any stage of this process?
No, we have looked not only in the optical, we have looked in the UV as well, because the optical monitor on board XMM has also UV capabilities. So we did a few light curves, continuous light curve during the XMM Newton exposure where QPEs were present, and we couldn't detect any variability in the UV. So we are confident that nor in the optical nor in the UV, these things show up as QPEs. This might be due to the fact that they shine. Let's say they stand out with respect to the disk at higher energy because the disk is cold. The disk has a 50 eV, let's say, temperature. These things have 100 eV temperature. So in a given X-ray band, they really stand out. Well, if you go in bands below, let's say 0.2, 0.1 kiloelectron volts, you are really very much dominated by the disk. So it might be tough to see them even if they were there.
Yeah, so there are limits And do you have those limits in a paper or something like that?
No, we didn't put yet limits because we wanted to have, now we will have a very beautiful optical light curve, and so I will give limits for the optical and UV simultaneously next paper.
Great, thank you.
Yeah.
Hi, Giovanni. Thanks for the talk. One of the things you didn't mention was the final observation before the second quote unquote TDE, where the QPOs during that final epoch seem to be a little weird in terms of the properties relative to the earlier epochs. It's almost as if the QPO mechanism is anticipating that there will be a second X-ray flare. I guess you could speak to, so what is the relative timing between that last observation and when we start seeing the rising X-rays? And maybe you could speak a bit more to that last epoch and its properties.
Let's go there then. Let me take one. Yeah, for instance, this one. Okay, so this last yellow observation, we believe it's really preceding by a few days the start of the second tidal disruption event. There you don't see all swift monitoring. I mean, we have combined a few observations, but if you looked at the individual observation, you can see that it starts really after this yellow thing. Okay, here the QPO is still very standard. It's true that you cannot really, I mean, you can see it even here, but when you fold it, it really stands out very clearly. What is strange is this violet observation. So this one has different properties. I didn't mention it on purpose because it would complicate things, but actually it shows, let's say, truly intermediate properties, in the sense that QPEs are very much weaker than in this yellow case, okay? And the timing is also different. So, but different not in the sense of the last observation where you just see some shift in the recurrence time. Here, it's really weird, okay? Which we interpreted, or at least we suggested, could be due to the fact that a TDE occurred, so the disk is perturbed, and if QPEs are due to the interaction of something, a secondary or mass streams from a secondary or whatever, and the accretion disk, you are here in a highly dynamical situation where the accretion disk, a new accretion disk is forming, but the other one is still there. There are shocks in addition to the normal ones, possibly very fast precession and things like that. So the fact that we didn't interpret completely this observation, but it might hold a clue on the dynamics of the disk formation, although it's just 4 QPEs. You don't have a clean sample of orbits to follow, but it really indicates that something strange was happening here. I mean, that this is not just a rebrightening of the mass accretion rate on the disk. Something else was happening. So this, let's say, gave some support to the idea that there was a partial TDE there. I don't know if I answered the question.
Oh yeah, no, thanks. I think it's quite, it's quite intriguing. Thanks.
Yeah.
Go ahead, Sue.
I was going to say this light curve is actually looking a little familiar to me. We actually have some optical TDE light curves that have a secondary bump. And so I'm curious sort of the connection between what is powering that rebrightening.
Yeah. Yes. What I can add here is that I didn't show. I mean, we have said that the QPE don't show up in the optical nor in the UV, but of course the quiescent level, which is this light curve, could potentially show up in the optical or UV. And what we see in the simultaneous optical monitor data is not exactly what X-rays show. In the sense there is a potential initial decay, but lower significance. And then the second rebrightening is not really tracked by optical nor UV. So in general, broadly speaking, this is much more striking in the X-rays than in the optical UV, which is a bit not annoying, but strange in the framework of standard TDs. Not only timescales are huge, but also it appears that I should say that these galaxies are likely dominated by a stellar cluster, so it might be difficult to get at the star at the nucleus with the optical monitor. So this is a possibility, so that there is heavy contamination, so that we don't see the variability. But still, optical UV, let's say, are much less variable even on long time scales than X-rays. So this kind of behavior is striking in the X-rays and not that significant nor in the optical nor in the UV.
I can ask just the follow-up question.
Yes.
Can you get any constraint on the peak of the optical disk emission?
No, basically no. What we have are simultaneous observation to this round, to these circles. Okay, beside this one that is an XMM slew, we have an observation here, and then the next is there in the optical and UV. And so we can't really say. What we can say is that it appears that the optical is a slightly higher level here than here, and then it goes like more or less constant afterwards. But we don't have the cadence to be able to say that, to see anything. And we have looked of course in the archives and Assassin, etc., and we don't see anything significant. Okay, so we believe that there's nothing striking in the optical with respect to this kind of behavior. Also mind that this is just overall in 9 years a factor of 3 in the X-rays. So in the optical would be tough.
2 questions. First, for the TDE experts, is there any TDE in a very low mass galaxy, which this is, which is just bright in the X-rays, not in the optical? I thought, if anything, the X-ray bright ones tended to be somewhat more massive galaxies, not really low mass galaxies. Is that any experts want to?
There's a claim in, oh, I'm not an expert, but I'll just say there's a claim in this Weaver's paper from 2019 that there is a population of very low mass X-ray bright TDs. I don't know if that's held up, but there also seem to be a population of higher mass ones above the optical sample.
I think the problem is that for the TD candidates in the lowest mass galaxies that we've seen, we just don't have good optical data monitoring. Monitoring the outburst or the early time of the X-ray flare. So we can't say for sure that there's been no optical flare associated.
The optical flare, as Stevie pointed out yesterday, precedes the X-ray emission. So anything that's detected in X-ray, by definition, could miss the optical.
But there are claims of intermediate mass black holes in disrupting stars in dwarf galaxies.
Sorry.
I had a different question about the QPOs. So if the intrinsic QPE light curves are not Gaussian,
are not, sorry, I didn't.
If I understand correctly, you're inferring the QPO by fitting Gaussian light curves to the flares and inferring that there's some residual timing on a similar time scale that you're calling a QPO. But won't any deviation of the true light curves from Gaussian lead to residuals at the time scale that you're seeing residuals at?
Yeah, yes, in a sense. I would like, look at the original light curve. So the QPO is basically this thing, okay? So this is less evident just because the symbol size is huge, but there is some excess emission in between 2 QPEs. Then if this is because the QPE has this shape, intrinsic, so like a burst followed by something longer lived, that's fine. It doesn't necessarily need to be a QPO of the quiescent level. So I call it that way, but I said it in the papers that it could be, for instance, a secondary QPE, a response of the first QPE of some kind, or a genuine oscillation of the accretion disk, so the quiescent emission. But you're right, we don't know exactly what the shape is, but if you limit the QPE to this huge burst, there is clearly some excess emission in between. Then if this is let's say the distribution goes like that of the flare, that's fine. I mean, I'm not, I would not have anything against it. It's just what we see. It's clearly something in excess of the burst, and it happens exactly between every QPEs and more or less with the same delay of about 1/3 of the period of the recurrence time. Then what it is needs to be understood, and it could well be that the real intrinsic shape of the QPE, the profile of the QPE, is comprising a sharp burst followed by a longer lived one. That's possible.
Without injecting too much interpretation, we did actually propose a way you could do this in this collision model. So essentially, when this, you know this, Giovanni, you sent it to, but when the star goes through the disk, it ejects the material roughly with the orbital speed. And since it takes 2 pi r over v to go around, you get one of these every pi r over v. So the debris that's going out with the orbital speed will go down to the black hole in about the QP period divided by pi.
Yes.
So indeed, it's about 3 hours, which is when you see this. So if you postulate that there is a collision and that shoots matter down to the central quiescent black hole, then you naturally get this delay.
Yes, I would agree. I agree completely. I think that this idea faces more or less the same problem as direct mass accretion through mass transfer, say at pericenter. I mean, there is a disk, so this matter will come down not to the black hole but to the disk, unless you are in a very favorable orientation. So I guess that if we want to interpret these features, both the QPEs and let's call it secondary QPE for this QPO. In this case, it would be a secondary effect. We should probably look at shocks between streams and disk, or between orbiting bodies and disk, rather than accretion, because this would work if there was no accretion disk. Then you would accrete matter directly. Otherwise, you will certainly increase the mass accretion rate inwards of the impact of this returning matter, but this will imply a viscous delay and so on. So if you want to get at orbital period divided by pi, basically, you need to invoke something almost instantaneous, which would be when it returns, it shocks. I think that's, so the idea would be to try to do phase result spectroscopy of this QPO and to see if this also is consistent with an expanding region that cools down adiabatically, as the QPE seem to be.
I was trying to understand if there is something interesting to be done by analyzing the data, not by just trying to model the light curve itself, but looking at Fourier space if you have enough information. And the point being that when people were looking at the original quote unquote the QPOs in X-ray binary systems, then if I remember correctly, the modeling there would be done directly in Fourier space and proposing that the different QPO components would be modeled with Lorentzians. I'm trying to understand whether that would tell you anything or how the would eliminate what you're seeing as residuals. It looks to me by eye that if you were to Fourier transform that, there would be something similar to a Lorentzian, I guess, which and then if by eye in the light curve you were left with something more close to sinusoidal, that will show out like something narrower in Fourier space. And trying to understand if there's other ways complementary to look at the data that might be informative with other things that people have thought about QPOs before.
Sure, I think it's certainly something that has to be done. If you Fourier transform like light curve like that, you have like trillions of peaks. That's the problem. You have all the possible harmonics, and it's really difficult to. I mean, it doesn't look like a clean 1/f power spectral density with superimposed a couple of features. It really looks like a zero flat PSD with superimposed hundreds of peaks.
But it shouldn't, right? It shouldn't look like that.
It's
And why would you see hundreds of peaks? You should only see.
no, why I don't know. This is the first time I had looked in Fourier space to see if I could see something significant there. This is what I got. So I forgot about it also because we have the opportunity to study it in real time. I mean, you go to Fourier space also when you have thousands of peaks to analyze, and with such a short time scale that is difficult to get any information directly out of it. I think that in this case we can do that in real space, but of course we should try and see. Now that we have accumulated more data, it could be a good idea to have a look at that.
Yeah, we have to start the discussion now. Thank you, Giovanni, very much for joining remotely.
Thanks. Thank you.
Stay on Zoom.